Thanks. Hello. This is a standard illustration that we can find under bias variance problem description. Are you more or less familiar with that plot? Okay, so I will explain briefly. So that line is our model, those dots, this is our data. At the first plot, the line cannot fit the data completely. This is a poor model of our reality that is represented by that data. The middle plot is like quite good. It is what we want. The model can fit data, but not too much. It can actually generalize well. And the last plot is the model that fits data completely. These are also the plots that caused me to dig deeper into our today's topic. Memorizing is not learning, but it is also a kind of skill, and it indeed might be used to learn our training set, our data by heart. But it is good or it is rather bad? And what can happen if we produce overfitted model and give it to users? I hope that it will be more clear at the end of this talk. AI can now outperform human intelligence in many domains. You may be familiar with those competitions, AI beats human champions. They marked a significant advancement that happened far sooner than experts expected. But it is a starting point for many discussion about high-level security concepts and also about the scenarios when intelligent thinking machines are taking over humans. But artificial intelligence has also many much more down-to-earth applications and also problems on technical ground. In terms of security and privacy, we heard on use of AI by both sides, by attackers and defenders, and how they may use AI for their purposes. By those who are in defenders' camp, AI might be used, for example, in malware detection or in network intrusion analysis. On the other side, cybercriminals might craft more sophisticated attacks like impersonation of trusted users. Messages written by AI software will be impossible to distinguish from genuine communication. And finally, AI might be exploited itself because of algorithm vulnerabilities. And here implications range from flooding people's mailboxes with spam when it was spam, the filter detector that was hacked, to even harming human life when it was autonomous vehicle that was attacked. And this is what I will be talking about today, the privacy and security of AI itself. This is our agenda. We will start from introducing basic concepts that will be used often later on, so it is important to have good understanding of them. Then we will go through some attacks examples, and at the end we will discuss possible solution to defend our AI. So let's get the terminology right. Artificial intelligence, this is a broad concept, and this is a science, not magic, of making things smart. Smart in the way that human are. In other words, it is teaching machines to performing human tasks that require intelligence, like natural language processing or face recognition. Machine learning, it is one of solution to solve AI task, and machine learning produce often models. Those models teach on our data. They are making decisions based on data rather than on algorithm, can solve different artificial intelligence tasks like clustering or classification. And I will also talk a lot about those models today, mostly classifiers, because we see them really often. And those classifiers are a kind of function that, given a input data without label, will return the assignment to a category. For example, if we have model trained on customer shopping history and we ask that model, will this customer buy that product, the model will respond either yes or no. And Deeper, we have neural nets. This is one of machine learning algorithm types. It is inspired by the biological neural nets that constitute animals' brain. And finally, deep learning, it is like modern approach to neural nets, basically new architecture, which is deeper, requires more computer power, and it can not only recognize patterns, but even patterns of patterns in highly dimensional data. This is currently silver bullet for image recognition task. Knowing that, let's try to answer our first question. Where and how AI might be attacked? This diagram will be to give you a brief overview where actually the attack might take place. Every machine learning algorithm requires data. In this database, we have rows. Each row is separate learning example. It is represented by features, which are in columns. And this data is also labeled. For each row, we have class assignment. We know to which category that row belongs to. And we have also our algorithm that we've chosen based on our task specification. This algorithm is trained on that data during training process, during learning, and the output of that process is model with learned parameters. And from now on, we have our prediction function ready. We can provide that model with learned parameters with input without labels, and it will return as a class assignment. And such a model can be deployed to production environment. And then, final user can start to use it. If they send a query with an unlabeled data, the server will respond, giving them back a category, a class label. And we can divide it even at higher level. Everything what is on your left side can be called development stage, and everything on the right is a production stage. And going back to our question, where the whole thing might be attacked. What do you think? Which part is the more vulnerable one? Okay. Actually, both are. Every stage of that pipeline may fall victim to different type of attack. But as we have to start with something, let's consider the attacks that happen during development phase first. They are also called Trojan-based attack. And Trojan Model is like this horse at the first sight, quite tempting. It looks normal. There's nothing wrong with it. And it may even be a kind of gift for a model developer, like transfer learning is. And the main difference is deep inside the model values of parameters, somewhere in the matrices. Those are often incomprehensible for human, thus we would most likely not look at them at all. And this is leveraged in the idea of triaging. It's the same like for normal software, to design such a way to change model behavior in some circumstances that the existing behavior stays unchanged. Having access to some parts of this stage, the attacker might craft a couple of Trojan-based attack types. And this might require various extent of knowledge about what is happening here. The attack might be done with white box approach, when the attacker knows everything about our training set, about our algorithm, and about the model with trained parameters. Or may be done with black box approach, when the attacker knows hardly nothing about what is happening here. But what those attacks in this category have in common is the fact that they require access to retraining. They require the possibility to modify the model somehow. The first type of Trojan attacks we will consider is poisoning. And this happens only when we are using continuous learning on data that comes from user in a real world, in online API. And this may be applied to various types of model, basically any type of model, whether it is a recommendation system or chatbot, may fall victim to that type of attack. This is TIE. It was released by Microsoft in 2016, and it was meant to be an experiment in conversational understanding. At the very beginning, Tai was greeting humans like that very cheerfully, and Microsoft said that the more you chat with Tai, the smarter it gets, learning to engage people through casual and playful conversation. Unfortunately, the conversations didn't stay playful for long. Soon after launch of Tai, people start tweeting the bot with all sorts of misogynistic, racist, and any other awful remarks. So Tai, using her learning capabilities, started to repeating those in the same way back to users. Uh, do you remember the date from the previous tweet? So, how long it took to convert innocent, friendly Tai to racist? Microsoft had to shut down the service 16 hours after its launch, and they put really a lot of effort to delete all incorrect tweets, but we can still find screenshots like this, and I can imagine that while cleaning all the mess done by Tai, they learned by heart that garbage in, garbage out. And to explain in general how this type of attack works, we can consider SVM classifier, and this might be used for various types of tasks. Here we have two-class separation problem. Here we have margins, support vectors, and our decision boundary. How SVM classifier is trying to separate those classes? It is trying to came up with such a decision boundary that the space between those two classes is as wide as possible. And this model is also incredibly fragile in the presence of any type of poisonous data, because the boundary is fully specified by those vectors, which are indicated by usually very small subsets of training examples. So here we can see that our support vectors are based on one example from this class and one example from this class. Can you imagine any way of changing those points location that will cause decision boundary change? We can change for example one point location like that, and from now on in that triangle it is like the change of decision boundaries. So all points from the area in that triangle were previously classified as a blue class, and from now on they will be classified as a red class. And assuming that we have such a model deployed to some API, such attack can evade the service availability, because at some point there will be so much bad data points injected that the boundaries learned during training process will become completely useless. And exactly the same happened to Tai. Yeah, but assuring training data quality is not enough, because it is a common practice to use pre-trained models which are ready to download, and they were trained through long days on huge data set, and we can only grab such a model, download it, and fine-tune to new task. And transfer learning led us to achieve state-of-art results within a couple of hours on single GPU. But what if those models are not so trustworthy? One task that benefits most, I would say, from transfer learning is face recognition, image recognition in general. And face recognition system based on deep convolutional neural nets are used to facilitate secure transactions or to control access to some sensitive areas like archives, laboratories, offices. And what if somebody can get access to somebody else's bank account which is protected by AI? Yep, researchers proved that it might be done, and it might be done by backdoors added during training phase. And backdoor leave your classifier functionality exactly like it should, with one exception, that backdoor. And backdoor is a type of input that the model designer is not aware of, but the attacker might leverage that input to make the classifier to do what they want. One type of backdoor is Trojan trigger. This is a small piece. I don't know if you see it properly. On each of this picture, there is like small modification, the same like a stample or sticker. Uh, and this is that Trojan trigger. And that Trojan trigger will cause the modified attacked network to generate Trojan target label. That trigger will cause substantial activation in some neurons inside neural net. And that substantial activation will lead to certain output. And this output is called Trojan target label. This is the output that the attacker wants Trojan model to generate. And basically any valid input sampled with those type of Trojan will cause the mutated neural nets to generate Trojan target label. And how this trigger is constructed, if we consider that those red neurons are representing some features, they are representing some pixel configuration, we want to construct this Trojan trigger in such a way that it will possess strong presence of that features which are represented by those neurons inside neural nets. Yeah, I think that now you have a brief understanding what can happen here. So we will switch to the other side, to the issues which may occur here on production. This is second type of attacks in our taxonomy. Those attacks are also called adversarial attacks. And they occur after model have been trained and they seek to take advantage of static parameters distribution, either by providing a specially crafted input or in any other way that does not require access to retraining to the modification of model. And the first type of adversarial attacks is evasion. And this attempts to fool model by providing that malicious input which was formed by applying small but intentionally worst case perturbations. And this is like the most the researchers are most interested in that type of attacks. It is over 300 papers about it so far. So this topic deserves a whole new talk, which will take place tomorrow. Tomorrow before lunch, adversarial examples will be investigated deeper, and I warmly encourage you to come. And there will be also a workshop also tomorrow. I know that last week there was still 3 places available. I don't know how is the situation now, but if you want to attend, you should ask organizers. And I believe that it is really unique opportunity to gain a little bit of more hands-on experience. And I've also warmly encourage you to attend. Adversarial examples will be covered in detail tomorrow. So now we can talk about model parameters theft. So say, for example, that we have machine learning as a service deployed somewhere on the server, and user can upload image or any other type of input and get classification. And this is a black box approach. The user knows nothing about the architecture of our model, about our training data. He can only upload image and see the output. And the user might ask for classification many times for many different samples. And by the same, he can build his own training dataset, which will be labeled by our models. And this enables him to teach his own model to respond in the same way as the original model does. And this means that he can actually obtain the estimates of parameters of our models. But why somebody wants to do something like that if there is already service with that model provided? Well, they maybe pay per query policy established, or the model itself or data it was trained on might be confidential. For example, for security application like fraud detection, the model confidentiality is critical for its utility. The attacker that can learn the model can often evade detection. And moreover, it is also a possibility to use model to extract information about training data. And yes, depending on how we build and train our models, sometimes it is still possible to reverse engineer what the machine saw during training phase from its memories, parameters. And that opens up a few new avenues for privacy attacks. The first and the simplest one is the membership interference attack. This is when the attacker has data point at hand and wants to know if that data point was used to train a particular model. And considering whether that golden retriever puppy was present in our training set might be perfect academic example, but what if somebody wants to know if some other person data was present in confidential medical list? When a record is fully known to an adversary, learning that it was used to train a particular model is indication of information leakage through that model. And this might lead directly to privacy breach. And for example, knowing that some patient clinical record was used to train model associated with some disease, for example, to determine the medicine dosage, may be an indication that this patient has this disease. Yeah, so interfering if someone is in or out is interesting. But you are probably wondering if it is possible to reverse engineer the underlying data that was used for training, having just black box access. And the answer is yes. Such attacks are called model inversion, and they try to extract an average representation of classes used during training. And they are unable to extract individual training examples, but still the results are pretty scary. Similar to membership interference attack, this attack also needs API access with some confidence intervals and can be run as a series of progressive queries. Previously, I said that it tries to extract an average representation. In the case of that model, one class is one person. We have a lot of picture of one person to train our model, and one class is not one person is not one example, is one class. So we can extract an average representation of the person. And to begin that attack, the attacker might use base image, which is like average human, or he can pick a closer image if he know anything about the gender or the age of that person. And then the attacker can run the model inversion as those progressive queries. He will modify picture in such a way to get higher confidence intervals, and at some point high confidence intervals are reached, and this produce results similar to that on the right side. This is an average representation extracted from the model. It is not perfect, but it is fairly demonstrative of how the person looks. This is the original picture of the man. I hope that you are not getting pessimistic about after listening about such a range of possible attacks, but if yes, we are now switching to brighter side. We have defenses, and in this part I will cover solutions specific to AI field, but it is still worth to notice that AI is mainly provided as a software. So best security practices known from software developers are still recommended. So monitoring your API usage or limiting usage of your API and validating that only valid input data was used to train model, or even checking your error distribution uh, that model returns are still valid, and they are recommended to provide basic security in machine learning applications. Among more sophisticated privacy security means, we have federated learning, and this is a way to incorporate more privacy in crowdsourced learning scenarios. And the key idea is, why even bring all data together if we can devise such a way that will let us to learn from subset and then effectively aggregate our learnings. Federated learning allows individual nodes, like those smartphones, to compute the parts of models and then send the portions back to be combined to constitute one aggregated model. And the individual user data doesn't have to be transferred. And federated learning models are hyper personalized for particular users. They involve low infra overheads, minimum latencies, and they are privacy preserving by design. And this allows learning in quite interesting situation. For example, when a group of hospitals may want to use machine learning techniques to improve the healthcare about their patient, but they don't have enough data to do it on their own, or they might be not so willing to release the data for central aggregation and analysis, they may apply federated learning, and this is like ideal scenario for doing that. Another way of adding more security into machine learning is differential privacy, and it was designed for statistical databases, but much of current work on privacy guarantees of machine learning solution leverage that concept. Since we already know that the attacker may retrieve our training set from our model, which the training set, which is a kind of database, we may apply differential privacy to protect us from extracting those sensitive information from our model. Consider we have database with employees data. We want to do some statistic on it. For example, we might be interested in calculating an average salary. This average is calculated over aggregated data, so like no private records are involved in it. So we are safe. There is no privacy breach. There's no problem. We can make such a result public. And then somebody leaves the company. The average salary changes, so we have to recalculate it, and then we can publish again. And privacy is broken now, because the salary of the person that left the company can be retrieved from our previous results, like that, doing very simple math. And here differential privacy comes in. And the idea is to make access to database randomized. And thanks to that randomized access, the presence of particular person will be impossible to distinguish from results of a query. The results of a query should be statistically indistinguishable. In above illustration, we achieve differential privacy when the adversary is not able to distinguish between the results returned by randomized algorithm based on data of all three users from the results returned by the same randomized algorithm but based on the data of two of the three users. And while differential privacy is not an algorithm itself, it is useful to think about it as a piece of software that lies between the adversary, in that case, or any other analytic, and the database. In a scenario when applying that differential privacy. An adversary sends a query to that intermediate piece of software. We will call it privacy guard, and the privacy guard is assessing the privacy impact, the sensitivity of that data. It is helpful to understand how much individual user data influence the result of calculation. And then privacy guard sends the query to a database. The database responds and gives the privacy guard the unmodified response based on data that was not distorted in any way. And then the privacy guard is adding noise to protect the privacy of individual users which are in that database. That noise is called to that privacy impact. And then the imprecise response is returned back to the adversary. In that scenario, the adversary can not learn anything about any particular user, so any private data was exposed. And differential privacy provides a general technique that can be applied in various ways in machine learning context. And the private aggregation of teacher ensembles is a framework that allows us to do secure machine learning on training data which involve user data, the data of people. And this means that we want to have the randomized, not access to database, but randomized learning algorithm. So the parameters learned by model will have the same randomized statistics, whether any individual user was present in our training set or if it was excluded. And the framework works like that. The big data set, the whole training data of user, is divided into separate partitions, and on each of that partitions another model is trained. The name of that model is teacher. It may be whatever model you can imagine, but the key idea is that the partitions has to be separate. And the overall prediction is generated by combining the results of individual teacher. It is like normal ensemble, and it itself does not add any privacy ingredient into the mix. But this is accomplished by another two important steps. Firstly, the noise is added. So the overall prediction is not like normal ensemble, but it is a noisy aggregation of individual teacher prediction. And secondly, those noisy predictions are used to label the unlabeled data, and then there is another model trained on top of that, the student model, which is trained on data that was privatized by adding that noise. And it is that student model that is exposed to end user for consumption. And the student model is not only private, but it is also really likely that it will have better performance than model trained in traditional way, because differential privacy, normally considered as a performance overhead, can be in machine learning can be utilized to make better models. It is well aligned with goals of machine learning. And how can it be? Do you remember that plots? We thought that memorizing is not learning, and memorizing a particular learning point is also a violation of privacy. So it is not only a form of overfitting that harms model generalization performance, but also it is a privacy issue. And here, when we reduce that privacy issue, we are reducing by the same the overfitting. And many teachers agreeing on the same label indicates the confidence in correctness of that prediction, because those teachers were trained on separate partitions of data. Differential privacy might be also used on local machine. In iOS use cases, Apple uses three key mechanisms to protect user data while still learning general patterns of the user behavior. For instance, if they want to determine which emojis are gaining popularity to add them to the quick access sets seen by all users, they can do like that. For the query, which emojis are trending, they first they are first using hashing, so that the backend service cannot see any direct identification of the users. Secondly, subsampling is employed. So only a random subset of each user activity is reported. And instead of every data point that might be of interest, only a random subset is sent. And lastly, even for those records that are sent, noise is injected. So a specific user's patterns of keystrokes are only approximately accurate when the backend receives it. And even by using that such a threefold privatization and such threefold protection, Apple engineers are still able to improve their predictive quick access emoji set across different locales. And lastly, efforts has been also underway using cryptography to provide privacy guarantees in machine learning. Privacy by homomorphic encryption can be used to do computations directly on encrypted data without the need for decryption. When the data is encrypted in traditional way, it is impossible to do any meaningful computation on that. But it is not the case when the data is encrypted homomorphically. If we encrypt 3 and 5 like that, we can still do addition, like in this example, straight on ciphertext without the need to decrypt it to do addition of it. And then we can apply decryptor only on output of that addition done on ciphertext. And when we decrypt the output, it is the same as the calculation done on normal numbers. And with the widespread adoption of cloud computing, there's an often scenario that somebody who has data wants to outsource some computation on that data to a third party, but he does not trust that third party with plain text data. So homomorphic encryption allows to do meaningful computation on that data without the need to see encryption key or the plain text data itself. And in such scenario, the third party can do computation directly on ciphertext and then send encrypted data in encrypted form back to user. And that user, data owner, can then apply his encryption key, which were never shared with third party, and he will get the result in unencrypted form. Homomorphic encryption is really evolving field, and there are many performance issues and also some restrictions because homomorphic encryption cannot be applied to non-polynomial functions and also can be done currently on integers for addition and multiplication. As we know, machine learning models often require floating point computation, and activation functions are often non-polynomial. So this means that there's a lot of challenges to overcome. But with the rising popularity of machine learning as a service, there's a lot of interest in that field, and people are trying to improve current homomorphic encryption algorithm and apply it to machine learning solutions. And there are two variants, and both are explored. The first variant is to perform homomorphic encryption learning on plain text data when we have model parameters decrypted and the math that is doing backpropagation, forward-backward passes is performed on that homomorphic homomorphic numbers, or in the other way, the model itself is in the plain text, but the learning is performed on encrypted data, and the same for prediction. We can give an encrypted input to a model. Yeah, this was the last defense that we've considered today, and of course I haven't discussed all possible security means that are available now, but you may notice that there is much more attack types than the defenses. And I didn't put it in that presentation that on purpose. It is simply much more research papers on attack types, and this means that we still have a lot of work to do, and maybe there are also some 0 days attacks that we are still not aware of, but at least there is a little, if any, chance that the thinking machines will take over humans in upcoming few years. Thanks.
Thank you very much. So if we can move on to Slido, there is quite a few questions. The later we are in the day, the more questions we have. Excellent, but I'm not sure when we're going to end then. On the left, the tab on the left, Q&A. Yep. Okay, cool.
Okay. How do you know if the model you are using does not have backdoors? Oh, that's a very interesting question. If we are considering backdoors, it is normally that in the papers that I've seen, they were doing it like that. They were retraining model with those adversarial Trojan input. So when we are performing prediction, when we have that model deployed and we are using it, normally the distribution of errors is quite even. So when the model is making misclassification, it is misclassifying the input evenly for each class that he was trained on. But it is not the case when it is a backdoor in a model. When it is a backdoor in a model, the model is skewed towards the input that is the Trojan target label from the example that I've discussed previously. So if the attacker puts some backdoors, we will see it in the error distribution. It is not perfect solution for all backdoor types, because when we have that model already deployed, we want to immediately know, for example, from parameters, if it whether it has backdoors or not, but we can only learn it knowing the proper labels for our inputs, because we know when the model made a mistake. Can you please explain how the model extraction attacks is done? Model extraction. Okay, you mean the membership interference. So this is the first type, membership interference. How it is done? In the research that I saw, it was done with black box approach, and what the guys done, it is really fabulous, because they designed two another neural networks, one to shadow the original neural network, and it was a network that was trained to perform similar attack type. It is not the requirement that the network has to be trained on the same data set. It is only better to train it to the similar task. And when they have that neural net trained for the same task, then they train another neural net called attack to distinguish between those records which are in or out of our training set. It might be done because the models are typically returning different classification vectors with different frequencies of the classes for the examples that they seen in training phase. So if the model saw some example during training phase, the distribution of classes that with the confidence level is slightly different than the distribution of classes for the model, for the input that was never seen by the model. And the attack network was doing that two class classification. By the attack network was recognizing if that class distribution is produced by model with input that was in training set or out of training set. And this is also connected to overfitting problem, because the models which are overfitted, they are more likely to have big differences between those distributions for input samples which were in and out of training set. Okay. Are there already some real-world high-profile face recognition attacks? Face recognition attacks, I'm not aware of if it was a research done but I know that there was a research done for person detection. You may be familiar with the YOLO architecture. It is a object detector, and there was several research about it, and the guys managed to do it with black box and also with white box approach, and they achieved quite high misclassification rates. And this type of attack is able to successfully hide a person from a person detector. And I don't know if it is exactly of any example exactly for face recognition system, but at least I know that for human it works, and this task is even higher because it was able to evade a system that that does the detection of class that has intra-class variety very high, because we as a human differ a lot, and if we are evading face detection, it is easier because we have a lot of because in one class there is smaller variety. So I believe that this type of attacks also has some application, but me personally, I didn't read any research about it.
Just one more thing. I'm conscious of time. We're getting a bit late and we still have another talk. So maybe we just answer one more question, right? And we might take those maybe either later or offline, right? Okay.
So the next one, are there any solutions to detect backdoors? Yeah, backdoors we've already discussed. It is the best solution that is known now is checking error distribution. Okay. Isn't homomorphic encryption super easy to break? Super easy to break. To be honest, I'm not sure.
That sounds like an offline question then, I guess. Right?
This is a very good question, but I will investigate it, how breaking homomorphic encryption works, and you can approach me later.
Okay, and I guess yeah, we really have to move on to the next one. So maybe the people that asked the question, maybe if you can just come up and just ask the questions. But again, thank you very much. That was really great.